Right, I would like to begin by thanking the organizers for inviting me to this wonderful meeting and for giving me a chance to present some of our recent results. But most important, I would like to thank many colleagues from France with whom we have been collaborating for a long time, Uriel Frisch, Marc-Etienne Prachet, Jeremy, who's in the audience, Dario, who couldn't make it at the last minute, Yannick Ponty, and Giorgio Kristulovic, and Nicolas Besse's picture was supposed to be here, but I couldn't find it. But I found on his website this beautiful photo of the Observatoire de la Côte d'Azur, which must be among the most beautiful CNRS labs. And we are very happy that we have been able to collaborate with them for several years. These are various students and co-workers with whom I have worked on some of the problems that I'm going to talk about. That will become clear as I go along, and I would like to acknowledge support from these funding agencies, in particular for this meeting, the Indo-French Centre for Applied Mathematics. Here's an outline of my talk. I'll begin with elastic turbulence, a somewhat old problem, and then something new, binary fluid turbulence, and then a little interlude on 2D MHD, and then something new again, inactive fluid turbulence. I will then give you illustrative results and conclusions. You will see that even though the Reynolds numbers will be quite modest in these situations, we will see turbulence-like phenomena, and that will be because there is always at least one other control parameter which forces the system to go into a spatio-temporally chaotic and turbulent state. So some review here. It's well known that if you add polymers to turbulent flows, even at the level of parts per million, they lead to a dramatic reduction in the drag. This is very well known and is contained in several of those papers and many others. However, there is something which happens at low Reynolds numbers also, and it has been called elastic turbulence. What happens is that the elastic stresses in the polymers, they trigger instabilities, which then lead to a chaotic flow, which is also turbulent. The initial papers here, Groisman and Steinberg, and then there is a review. There's some numerical work from our group. And I should also point out that there were similar chaotic regimes seen in other systems, which, as far as I can tell, have received less attention than they should have. I mean, for example, there is low inertia turbulence in worm-like micelles. I think this is the first paper on it by Ranjini, Geeta Basappa, and Ajay Sood, and so on. So in contrast to conventional hydrodynamic turbulence, the examples of low inertia turbulence here might often not have an energy cascade through an inertial range and will indeed be observed at very low Reynolds numbers, and therefore have potential applications in microfluidics to stir up things in microfluidic assemblies. But I won't get to that today. So here is the first paper, Groisman and Steinberg, and here is his annual reviews paper, which will give you much more detail than I will. But let me now tell you a little bit about how to model such admixtures of polymers in a fluid. And this is done at some hydrodynamical level by solving a coupled Navier-Stokes equation, which is written here in terms of the vorticity, and there's a stream function here too. Don't look at all the details because there are too many details. I just want to give you a big overview of the field. And then there is this polymer conformation tensor, which has its own evolution equation. So it is advected by the velocity. And then there is a term here which encodes the so-called FINI-P model, that is finitely extensible polymers. And the important new parameter here is the polymer relaxation time. And if we non-dimensionalize things, the Reynolds number will be something called capital omega, and the Weissenberg number called Wi, will be a non-dimensionalized polymer relaxation time. To study these types of systems, I will often start them off in a flow which is called a cellular flow in fluid dynamics. It's a crystal of vortices and anti-vortices, which is enforced by some sort of external forcing. Right, there are various parameters. Please don't look at the details. I'll be happy to discuss them with you later if you like. Okay, again, the direct numerical simulation of this model is not for the faint of heart. I mean, you can't blindly use a standard pseudospectral code. You will get into all sorts of troubles. In particular, this polymer conformation tensor C has to be, symmetric, positive, definite. And if you don't use some clever tricks, you lose that property right away. And we then adapted a code that was written in 3 dimensions by Prasad and Dhruva Mitra, who were my students at that time, Anupam and I, and then we did it in 2 dimensions. And if you want the state of the art in this, I strongly recommend this paper. I don't know whether Jason is in the audience, and Dario also. They have examined several schemes for doing such calculations, and I'm happy to report that they find that the scheme we used is perhaps the best. Okay, now to change gears, I will also be looking at binary fluid systems. So you know this well, so just oil and water drops, and again, bubbles in a turbulent flow. We'll skip anti-bubbles today. And this is very well known to statistical mechanicians. We all grew up learning about the Cahn-Hilliard system, which tells us how 2 different phases, fluids A and B, phase separate. And we describe them as usual by using a Landau-Ginzburg functional, which has a double well potential here, V of phi, written in some non-dimensionalized way here with 2 minima, one at +1, -1, and large and positive phi is A rich and large and negative phi is B rich. And if we just live at this level, we have, of course, something we assign as a homework problem, which is this double well potential, and then there is a one-dimensional interface here, which you can solve for analytically. So that's the interface between the A-rich phase and the B-rich phase. But when the coexisting phases are fluids, then it does not suffice to keep only Cahn-Hilliard. You must add in Navier-Stokes, and believe me that if you do it properly, this is what you will get. You will recognize Navier-Stokes up to here, and this is the action of the scalar field phi, which we were just talking about on the fluid. We don't need this term today, and that's just friction, so that's for gravity. Again, incompressible, and this is the good old Cahn-Hilliard thing, but now with the scalar advected by the fluid velocity, all right? Again, you can see that there are large numbers of parameters, but one good thing this description has over the standard fluid dynamical description is that you do not have to enforce boundary conditions on a moving droplet boundary, for example. So this is a so-called diffuse interface model, and sometimes engineers complain because these interfaces are quite thin, but I think good mathematicians have shown that if you do things carefully, this diffuse interface description is a valuable one. The price you pay were not only Reynolds numbers, depending on the setting, there are many other control parameters. Today we will concentrate on the capillary number, which is related inversely to the surface tension. And that is the parameter we will tune to get to low Reynolds number turbulence in this system. Okay, again, you can do direct numerical simulations. I will not bore you with details. A little interlude. This is a point of view that has been advanced by Pat Diamond as his collaborators, that there is some formal similarity between 2-dimensional magnetohydrodynamics, where A is the scalar vector potential. I mean, in 2D it's a scalar. So here is Navier-Stokes, and here is how the magnetic system acts back on it. And then with the identification, which I'm not going through in detail, that you could define an effective magnetic field for the scalar 2D Cahn-Hilliard-Navier-Stokes system with this identification, there is a more or less one-to-one mapping. It's not exact between the 2D Cahn-Hilliard-Navier-Stokes system and 2D MHT. So perhaps we will be able to see something like this, low Reynolds number turbulence in 2D MHT. What is the additional control parameter? You see here, that's the magnetic diffusivity. You see here, that's the kinematic viscosity, I hope. But the ratio is the magnetic Prandtl numbers. The question is, you stick at low Reynolds numbers, but you change the magnetic Prandtl number, can you get low Reynolds number turbulence? So this is the paper which spells out the mapping. It's a very nice paper and I strongly recommend. Now, if you do these simulations, you find many things. I'll just give you a quick overview of some results that you would find for Cahn-Hilliard-Navier-Stokes. If you just ran a simulation with a droplet, let us say. So if the surface tension is large, you get a tightly sort of circular droplet, and if it is low, then it's a floppy droplet, and if you keep track of the perimeter of the droplet, you get these very, very spiky time series, which actually are multifractal, as we showed a long time ago. The other thing that turbulence does is it suppresses the phase separation that occurs in the absence. If you're below TC in good old Cahn-Hilliard-Navier-Stokes, the system would phase separate into an A-rich phase and a B-rich phase. Now, when the turbulence churns it up, you suppress that phase separation, and you can actually characterize it by defining a length which you can get out of a density-density correlation function. So that's just the background. So what the method that we will use, at least in some of our studies, is to first induce, as I said, a vortex crystal, which we did first for 2D turbulence by the application of an external force. And what we found in the 2D turbulence cases is that as you increase the amplitude of that force, that induces turbulence, which it's a completely non-equilibrium system, but think of it roughly as temperature. It's like increasing temperature. It melts the crystal in a way that would be quite acceptable to a condensed matter physicist. But let me not go to turbulence. So what I'm going to show you now is that even at low Reynolds numbers, by changing the Weissenberg number, so that's the new control parameter for the polymer case. So we have started this system off with a nice array of vortices and anti-vortices, and this is the description in Fourier space, so that's good old Bragg peaks. And then this is low Reynolds, but as you increase the Weissenberg, you go from a crystal, a steady square crystal, eventually to a state with spatiotemporal chaos and turbulence. Turbulence because the energy will be spread over many length scales, there will be vorticity, and so on. So this is low Reynolds number turbulence, very clean example. And I just wanted to emphasize that if you look at these things, this is not a noisy system. The system is generating its own noise, so it's not one clean transition. There is actually a whole bunch of transitions which are quite complicated. You can go through quasi-periodic states, both quasi-periodic in space and time, but I will not dwell on that today. I just want to point out that we have low Reynolds number turbulence here. Okay, so you can do a phase diagram. So this is Weissenberg number, this is Reynolds, and I'm telling you, if you look here, to the best of my knowledge, this was the first detection of low Reynolds number turbulence, and the Bragg peaks, they all get washed out. If you look in Fourier space, this is the real space. So that's how it, if you like, it's been melted by elastic turbulence. Of course, turbulence, everyone says, is intermittent, and indeed this is intermittent too, and I don't have time to cover it today, but I strongly recommend this recent paper, and they have characterized the intermittency in such elastic turbulence very well, this set of authors. Now, let me see if there is an interface-induced analog of this. And indeed there is. So we start with the Cahn-Hilliard-Navier-Stokes equations that I told you about. So we have this array now, not only of vortices and antivortices, but also phi-rich regions and A-rich and B-rich. And as you decrease the surface tension, there are significant interfacial fluctuations, and this vortex melts. Reynolds number relatively low, but the melting occurs because of interfacial fluctuations, right? So this is yet another example of a low Reynolds number turbulence. Again, I could go through all the time series and Fourier spectra to show you that this indeed does happen as you decrease the surface tension. Again, the detailed transitions, there's a whole sequence of them, you have to keep track, but eventually you do get a state with turbulence. You can play the same game with 2D MHD. I'm just showing you illustrative plots. These are simulations carried out by Sharad Yadav, and again, I won't dwell on it too long. There's also work by the Diamond group here on similar situations. Now let me quickly spend the last 8 odd minutes on other models, which are models for active scalar fluids. This is work done with Nadia Bihari Pradhan and Kiran. Kiran is now in NESS, so that's again more Indo-French collaboration. So, we looked at Cahn-Hilliard-Navier-Stokes. So that was the sort of Landau free energy functional we had. Again, now except that psi was phi. Now I'm thinking of psi as a concentration of active microswimmers, and this was a model that was introduced in this paper here for so-called motility-induced phase separation. I mean, don't look at all the details, but there is an extra stress term here with the coefficient zeta or epsilon. If sigma is equal to zeta, we are back at good old Navier-Stokes, but if sigma is not zeta, then it's a model for extensile swimmers. And if it is less than 0, then it's a model for contractile swimmers, for example, like C. Reinhardti. So we will consider zeta less than 0. And again, I want to show you that this sort of turbulence, which is induced by this activity, there is no external forcing, but it's active in the sense that Sriram and his colleagues have studied a lot. So, as you increase activity, the phase separation is suppressed more and more, and the Reynolds number is still quite modest. You can characterize the arrest of phase separation. I'm showing you a Reynolds number here, which is going up to about 120, but I remind you, this is very modest because this is an integral scale Reynolds number. If I actually looked at Taylor microscale Reynolds number, be roughly the square root of that. So again, low Reynolds, but turbulence. Turbulence meaning if you look at the energy spectrum, it is spread out over several decades of wave number. And if you look at the flow, there is vorticity in the flow. That's the good old-fashioned definition of turbulence, spatiotemporal chaos and vorticity in the flow. Okay. Perhaps I will skip this. This is something very interesting. You can get a self-propelled droplet, but let me save that for some other day. And then now let's look at some models for bacterial suspensions. So that's a vortex forming in Bacillus subtilis, and this is a dense suspension of E. coli inside a spherical droplet. So what are the types of models that are around for this? The simplest one is the so-called TTSH model, Toner to Swift-Hohenberg. And why do we have this? Because many active fluid systems show this emergent spatiotemporally chaotic patterns. And if you look at the equations, which I'll show you in a minute, you will see what they do. I mean, there are more complicated models. There's a whole variety of them. And the especially simple ones that I'm going to show you, you can find a derivation of those in this paper. Okay, so this is the thing, sort of like Navier-Stokes, but with a coefficient lambda here in the advective term, a gamma naught and a gamma 2. So this would be conventional viscosity, but it has the wrong sign, and this is the fourth order gradient which stabilizes it, sort of like in the Kuramoto-Sawaczynski model. And this is the Toner 2 nonlinearity, which in the mean field limit could give you a state with some mean velocity square root minus alpha over beta. But that's never observed really, at least in 2D, all right? And you get a complicated state, which is turbulent. You can do standard linear stability analysis and pick out different scales, length scales, time scales, etc. All right? And the terms which make this TTSH system active are this friction term, but it is anti-friction. There's a negative viscosity and also this parameter lambda, which is in front of the other terms. So I'll just give you two quick examples of such turbulence. So this, we investigated irreversibility in such bacterial turbulence in these TTSH models. I mean, all of you know that fluid turbulence is irreversible, but if I challenged you, I played you a movie of Lagrangian particles in a turbulent flow played backwards and forwards in time, you would not be able to tell the difference. This is just to show you the sorts of patterns we get for this TTSH turbulence. And then to characterize the irreversibility, you really need to look at the skewness of certain probability distributions, like that of PAR or of energy increments. And I won't show you every detail here, but to make a long story short, what we found here is that for this particular type of bacterial turbulence, the skewness is the other way compared to conventional fluid turbulence. So, you gain energy faster than you lose it rather than the other way around, which seems to be the case in conventional fluid turbulence. Now, the last thing I will do in the remaining 2 odd minutes is to tell you about intermittency, which is some joint work done with Shamriddhi, Kunal at ICTS, Anupam at IIT Hyderabad, and Kiran, who is now in NESS. And it builds on some earlier work from Shamriddhi's group on the same model. So I remind you that we were tuning the activity by changing this parameter alpha. What Shamriddhi and his colleagues showed that if alpha is large and negative, you get into this, what they called a state of maximal chaos with an emergent universal state of active turbulence. You can then ask, does it show intermittency? I will remind you that the simplest way to characterize intermittency is by looking at velocity increments, velocity at point x minus velocity at point x plus r. You take that difference, raise it to the pth power, find it in the statistically steady state. And then you find the scaling exponent zeta p, which r to the zeta p. And if zeta p is a nonlinear function of p, then you say, aha, that's turbulence. And we showed it not only for the Eulerian fields, but we also showed it for Lagrangian particles by looking at increments along the Lagrangian trajectory. And in every case, we do find clear signatures of intermittency, which had not been seen earlier. And there are some details which make it look a little like fluid turbulence, but I will not dwell on that now. So let me just end by saying that we have examined 4 types of turbulence at low Reynolds numbers, and in all these examples, the turbulence is induced by tuning one more control parameter. In elastic turbulence, the Weissenberg number, 2D MHD, the magnetic Prandtl number, interface-induced turbulence, the Weber number, or the inverse of the surface tension, in active fluids, the activity, and we have compared these with conventional fluid turbulence. So with that, I thank you for your attention, and I'll be happy to answer any questions that you might have.
Thank you, Rahul. The timing of the talk was impeccable. It was Gavaskar style. Okay, the Indians will understand that, but nobody else. Okay, so questions?
Yes, Sriram.
Yeah, Rahul, you identified the parameter, the coefficient of advection in the velocity equation in the last bit.
Yes.
With the type of active stress, contractile versus
right. Yes.
extensile. I guess that implicitly assumes that sort of your active orientable elements are aligned with the velocity, I guess.
Yeah, that's the limit in which you get TTSH. Otherwise, you have to do the more complicated models, which you know much better than I, either polar or nematic, etc.
Right.
Yes, absolutely right. Yes.
So thank you very much for interesting. I mean, many examples. I mean, so I have a very general question. I mean, you know, when you show the simulations, do you actually go to the steady state? And did you show, you know, in some cases it looked like steady, but I mean, how would you actually make sure that they are in the steady state, or is that even, you know, an important issue?
No, we do. I spared you the details. We do, and we are careful. And when we quote things like multi-scaling exponents, they are obtained by averaging suitably over the statistically steady state.
I mean, are you actually really interested in the steady state? Is that an important issue?
We are. Yeah, this is a talk full of examples, not of the details, but I'm happy to share those with you. Certainly, we are, and we have lots of data and lots of...
More questions? So to a certain extent, there's a length scale at which you drive the system.
Yes.
And I guess, so if your system wants to coarsen, it's that length scale that cuts off the coarsening.
Yes.
Yeah. So if you drive it...
Yeah, we can fish that out, absolutely, yeah. And in some cases, it's completely transparent, like in the last one, where it was a balance between the second order and this fourth order gradients. Sure.
Okay.
Absolutely.
So thank you very much.
Thank you.
Okay.
Long live India and France friendship.